Welcome to Basics of Finite Element Analysis. Today is the third lecture of this week, and we will continue our discussion related to shear locking in this lecture. But before we discuss any further, I wanted to point out two errors. These are important errors which were made in the last lecture. So, the first error was that when I was defining these interpolation functions alpha 1 and alpha 2, alpha 1 was defined as x bar over He. Actually, this should be alpha 2, and similarly this should have been alpha 1. So, alpha 1 is 1 minus x bar over He and alpha 2 is x bar over He. So, this was one error, and as a consequence of that error got duplicated, and here again when I defined betas, then beta 1 was defined as x bar over He. Actually, that should have been beta 2, and beta 2 which was defined as 1 minus x bar over He, that should have been defined as beta 1. And the last error which flew out of this was that this term on the right hand side should have been W2 minus W1 over He. So, the conclusions are still the same, but because of these errors you will have a problem of signs, and that will create problems. So, but all the conclusions and the understanding remains unchanged. So, we had discussed in the last class the cause of this shear locking problem, and the fundamental reason why this shear locking comes into picture is because the order of our linear of the order of the element associated with W and that associated with psi, they are, in this case they have been assumed to be the same. If the order of W was 1 more than that for psi, then this problem would not have happened. Okay. So, the way we avoid this problem is, we can avoid this problem in two ways. So, we can avoid shear locking in two ways. So, the first method is that instead of having equal orders, that is m and n are same, we take m as n plus 1. So, in this method is known as consistent interpolation. Element CIE. So, in this case what we do is m equals n plus 1. So, if that is the case, then this mathematical locking which we saw earlier, this vanishes. But once we do this, we develop another problem, and the problem is that suppose you have an element, two noded element, and so for the same element which is He long, it will have two nodes for psi if it is a linear element, but for W the same element will have three nodes when I am doing the interpolation for W. Okay. When I am doing the interpolation for W, because m is n plus 1. Now, if n was 2, in case that is the order of psi, then m which is the order of W will be 2 plus 1 which is 3, which means that I have to choose a quadratic function, and if I choose a quadratic function I have an extra node in between. Okay. Now, what is the problem because of this? The problem is that when I do the assembly of all the elements, when I do the assembly, then it becomes tricky. how we add up all the correct terms at the correct places, right, because then we have to be very careful, and that becomes a tricky exercise. But from an interpolation and from a theoretical standpoint, this approach is just fine. It is just fine. But to avoid this assembly problem, people have come up with another method, and that is called equal interpolation. So, in the first case it is consistent interpolation. What does it mean? Consistent interpolation means that whatever interpolation order is, it is consistent with the mathematics required, right, and the mathematics requires that m should be equal to n plus 1. So, that is the consistent interpolation method. In the second method, which avoids this assembly problem, this method is known as equal interpolation. But reduced integration. But reduced integration element. RIE. So, here we equal interpolation means that we still take m equals n, m equals n. But if we just take m equals n and did nothing, then we would have the shear locking problem, which we have discussed. So, but we still want to avoid the shear locking problem, and because m is equal to n, the number of nodes are 2, whether it is psi or whether it is w, or if it is if n is equal to 3, then it is if n is equal to 3, then it is a quadratic element for w as well as psi. So, in terms of assembly, that issue is not there, but then we still have shear locking. So, to avoid shear locking, what we do is we do reduced integration. And I will explain that in a moment. Okay, I will explain that in a moment. To avoid, so we still take equal number of nodes, order is same, m is equal to n, but to avoid shear locking, we do something known as reduced integration on some specific terms. So, what does reduced integration mean? To understand this, consider this. So, suppose I have a curve, okay, and I want to find the area under this curve between 2 points. Okay. So, let us say this is my x and this is some function y. So, I want to find the area which is here. Okay. Now, if I consider only one point when I am integrating it, then I will get one answer. What does that mean? So, suppose this is y1 and this is y2. Okay. If I assume that y is constant, then the area is, if y is assumed to be constant, then area is equal to y1 times, suppose this is delta x. So, this is one estimate of the area. It may not be accurate, but this is one estimate of the area. And in this case, I am only using one point. Right? I am only using one point over the element to get the area. One point in this case is y1. Okay. If I say that y is assumed to be linear, then area is equal to y1 plus y2 divided by 2 times delta x. Okay. Here I am using using 2 points. So, I am using 2 points for integration, right. In the first case I am using only 1 point for integration, in the second case I am using 2 points for integration. Okay. I can extend this logic. If I assume y to be quadratic, then I will consider 3 points in the domain when I am trying to find the area, and we can work out the formula, that is not the problem, right. So we need 3 points. So the number of points which we consider when we are doing this integration, it tells us whether the function is constant or it is a linear element or is it a quadratic element or it is a cubic element. The number of points which are considered for integration defines whether the function is linear or constant or quadratic or so on and so forth. Okay. So these number of points in, and that is when we are doing, so in our differential equation, what are we doing? We are integrating over the domain of the element some functions, right. That is all we are doing. We are integrating some functions over the domain of the element. So what we are doing here is we are using equal interpolation. So that gets rid of this problem related to unequal number of nodes for W and psi, but for specific terms which have to be integrated, which relate to, which cause shear locking. So the numerical integration of a function is achieved by, it depends on the number of points considered in the domain of integration when we are doing that thing. Okay. So that is what we are doing. So what we are doing here is that there may be in our differential equation or in the weak form some terms. So these are the two weak forms, and some of these terms may be causing shear locking, and the shear locking is happening because we have assumed that m equals n equals 2. If this equality was not there, if m was more than n, we could have avoided this. Now in this case we still want m to be same as n, and that is fine, but then if there are terms, for instance this particular term which causes shear locking, then when I integrate the contribution of this term, I consider one less number of point when I am doing the integration. Now you will, how do we do that? We will learn it, but when I am integrating this term, then I evaluate the function at an extra number of points. When I integrate this first term, then I evaluate the function at one less number of points. So what does that help us? It helps us maintain the number of nodes is same for psi as well as W. So we do not have the assembly problem, and we still are able to avoid, because we have for specific terms we are reducing the order of integration. Okay. And we will learn a little bit more about this when maybe next week when we discuss numerical integration procedures called Gaussian by using Gaussian quadrature method. There also we evaluate the function at a certain number of points, and if it is a constant function, then we evaluate at 1 point. If we want to do a linear quadrature, then we do it at 2 points, and so on and so forth. So based on how many number of points we evaluate the function and use those values to compute the integral, that is the way we solve this numerical problem of shear locking. Okay. So that is how we accomplish this reduced integration. So we reduce the level of integration on specific terms, but when we are doing interpolation, we still have same number of functions. Okay. So, this method is called reduced integration method, or the element on which this function is carried out, this is called reduced integration element. So, I think what we will do is we will close this discussion at this point of time, and in the next class we will actually do an exercise on reduced integration, so that it becomes more clear to all of us. So, thank you, and we will meet tomorrow. Bye.